453 kilometers per hour. At this velocity, the air doesn't move out of the way, it shatters. You are looking at the fastest steel-on-steel machine ever forged by human hands, the CR-450. Why did China gamble $100 billion to challenge the laws of physics? Is it a train? Or is it a low-altitude flight without wings? To survive the sonic drag, engineers had to reinvent the very atoms of the fuselage. Witness the heart, an aerospace-grade magnesium, aluminum alloy, twice as strong as steel, yet 30% lighter. Look at this surface. It's cut by industrial fiber lasers with a precision of 0.001 millimeters. One microscopic flaw at 125 meters per second. And this 500-ton beast turns into a shrapnel cloud. This is quantum K manufacturing. Today, we dissect the engineering miracle that made aviation look slow.
This next-generation magnetic levitation train just completed its inaugural run, promising to revolutionize travel across the continent.
First, the friction. At these speeds, the air thickens into a solid wall of pressure. To pierce it, the CR-450 uses a shark-skin biomimetic nose, longer than any train in history. It doesn't push the air, it slices it, neutralizing the deadly piston effect before it even begins. But weight is the true enemy. Every bolt, every wire was re-engineered to shave off milligrams. The result? A silver bullet that accelerates faster than a supercar while carrying 1,000 souls. But the real nightmare begins in the dark. As the CR-450 screams into a narrow tunnel, the air is trapped. It compresses into a piston effect, a wall of pressure so dense it could shatter standard safety glass. To survive, the CR-450 breathes. Sensors detect the barometric spike, activating variable pressure relief slats on the roof in 0.01 seconds. Now, look beneath the skin. Witness the heart, the high-voltage permanent magnet synchronous motor. This rare earth powerhouse delivers a 20% leap in efficiency over everything the West has built. It generates raw thrust comparable to a squadron of fighter jets, yet it's light enough for a single industrial crane. But extreme power breeds hellish heat. Without the cryovortex cooling system, these copper coils would melt into slag. Aerospace-grade liquid coolant circulates through the core, keeping the atoms stable under impossible stress. Every superconducting cable is wrapped in heat-resistant polyamide, rated for a staggering 800 degrees Celsius. The mechanical tolerance of the rotating shaft? 0.01 millimeters. Smaller than a human red blood cell. At 450 kilometers per hour, the slightest vibration is a death sentence. The bogey would tear itself apart like wet paper. 500 fiber optic sensors act as the nervous system, tracking heat and oscillation 1,000 times per second. This data flows into the AI central brain, making life or death braking decisions in 0.05 seconds. But how do you stop a 500-ton steel bullet traveling at the speed of a high-velocity projectile? Conventional brakes are useless. The CR-450 ignites a hybrid electromagnetic and regenerative braking grid. 31. At 450 kilometers per hour, even the ground becomes unstable. To keep the CR-450 level, China had to build the world's most advanced infinite rail system. These aren't standard tracks. They are ballastless slab tracks, precast in smart factories with zero margin error. Every concrete slab is polished by robotic grinders until the surface is as smooth as a laboratory table. Why? Because at this speed, a deviation the size of a coin would create a vibration force capable of derailing the entire train.
As you can see behind me, the Apex hypersonic train is now fully operational, reaching speeds of over 500 miles per hour.
Look at the welding. This is thermite welding, a chemical reaction at 2,500 degrees Celsius that fuses steel into a single, seamless ribbon. Thousands of kilometers of rail with not a single gap. This eliminates the click-clack sound, allowing the train to glide like it's on a cushion of air. But the Earth moves. To counter bridge vibration, the CR-450 uses active suspension controlled by laser gyroscopes. These gyros detect bridge swaying and adjust the train's center of gravity 1,000 times per second. Now, witness the logistics nightmare, transporting 500-meter-long steel rails through narrow mountain passes. specialized transport trains snake through the terrain, bending the steel like a flexible ribbon without snapping the molecular bonds. On-site, engineers work under 24/7 high-intensity floodlights, installing the backbone of a new era. Every bolt is torqued to an exact specification, logged into a blockchain database for eternal tracking. This isn't just construction. It's the assembly of a low-altitude runway that spans across a continent. But the ultimate test isn't the track, it's the bridge. A 30-kilometer sea-crossing viaduct built to withstand a Category 5 typhoon. But the ultimate enemy of speed isn't just air, it's heat. At 450 kilometers per hour, the friction between the wheel and the rail generates temperatures that would soften ordinary steel. To counter this, the CR450 uses high-carbon vanadium alloy wheels, forged under 10,000 tons of hydraulic pressure. Each wheel undergoes a brimstone test, spinning at 500 kilometers per hour while being sprayed with molten salt to simulate 20 years of wear in 20 hours. If a single microfracture appears, the entire batch is smelted down. There is no room for good enough. Now, witness the stress test of the bogie, the frame that holds the wheels. Hydraulic rams oscillate the frame 10 times per second, mimicking a century of vibrations in a single week. This is the ghost in the machine, a digital twin AI that predicts failure before it even happens in the physical world. Every sensor pulse, every metallic groan is recorded, analyzed, and solved by quantum-grade algorithms. But what happens during an emergency? How do you stop this kinetic monster if the power fails? Enter the eddy current brakes. They don't touch the rail. They use magnetic fields to turn kinetic energy into heat instantly. Look at the thermal camera. The air around the bogies reaches 500 degrees Celsius in seconds. This is the price of safety-controlled, localized destruction of energy. Beyond the brakes, the CR450 must survive the deadly crosswind. On the high-speed viaducts, winds can hit 120 kilometers per hour. To stay on track, the train's computer-controlled wings adjust the downforce in real time. It's a delicate dance of physics, being light enough to fly, but heavy enough to stay grounded. Maintaining 450 kilometers per hour isn't just about raw power, it's about information. The CR450 is a rolling supercomputer. Every millisecond, the train communicates with a dedicated 5G industrial network, mapping the track 50 kilometers ahead. It knows every curve, every thermal expansion of the rail, and every wind gust before it even arrives. But this intelligence requires immense energy. Enter the high-speed catenary, a specialized overhead wire system. Traditional wires would snap or melt. These are high-tension chromium-copper alloys, pulled at 30 kilonewtons of force. This tension ensures the pantograph, the arm on top of the train, never loses contact, even at near-sonic speeds. Look at the interface. A continuous blue electrical arc, a constant flow of 25,000 volts feeding the beast. To prevent wear, the pantograph's head is made of self-lubricating carbon-copper composites that survive 1,000 degrees Celsius.
As you can see on screen, the new signalling system has drastically reduced delays across the metropolitan network.
This is why the train uses AI predictive pantograph control, adjusting its upward pressure based on real-time vibration data. Deep inside the power cars, massive silicon carbide inverters transform that raw voltage into precise frequency pulses. This technology reduces energy loss by 30%, making the CR450 the most energy-efficient high-speed vehicle on the planet. But energy must be balanced. When descending or braking, the train becomes a power plant. It captures kinetic energy, turning it back into electricity and pumping it back into the national grid. It's a closed-loop system of efficiency that redefines the 21st century energy economy. But where is this monster born? Welcome to the CRRC Gigafactory, a cathedral of automation spanning 2 million square meters. Here, human hands rarely touch the machine. Instead, an army of 2,000 synchronized robotic arms performs a high-stakes mechanical ballet. The process begins with friction stir welding, a solid-state joining technique that fuses aluminum plates without melting them. This creates a joint stronger than the parent material itself, essential for surviving the extreme vibration of near-sonic travel. Look at the precision. Every rivet is placed by an AI-guided vision system with a tolerance of 0.05 millimeters. Why such obsession? Because at 125 meters per second, a single loose fastener becomes a high-velocity projectile. Inside the cabin module, workers install a bioatmospheric shell, a multi-layered insulation that blocks 99% of outside noise. It is the silence of deep space inside a machine traveling at the speed of a bullet. Now, the marriage. The massive 2-0-ton chassis meets the aerodynamic hull in a single fluid motion. Laser alignment systems ensure the two parts are perfectly centered, with sensors checking the center of gravity to the gram. Every square inch of the silver skin is then coated with a self-healing ceramic polymer. This coating reduces skin friction by another 5%, slicing through the air like a hot knife through butter. Witness the final inspection. A massive 3D X-ray scanner orbits the train, looking for invisible molecular defects. If even a microscopic air bubble is found in the alloy, the entire 200-meter car is rejected. Zero defects. Zero excuses. This is the gold standard of 2026 manufacturing. 91. Manufacturing is only half the battle. Now comes the reckoning, the kinetic stress test. To ensure the CR450 can withstand the unthinkable, a prototype car is subjected to a hellfire simulator. Massive jet engines blast the hull with 600-degree air currents to simulate the heat of a high-speed desert friction fire. Does the magnesium-aluminum alloy hold? Sensors embedded in the skin track the thermal expansion down to the nanometer. Next, the ballistic bird strike test. A compressed air cannon fires a 4-kilogram projectile at the reinforced cockpit glass at 500 kilometers per hour. The impact force is equivalent to a small bomb. If the glass cracks, the design is dead.
The cockpit windows you see here are equipped with the very latest in navigation technology, allowing pilots to maintain situational awareness even in adverse conditions.
Witness the high-speed vibration test on the Shake Table A hydraulic rig that simulates a Category 8 earthquake. The bogies and suspension are pushed to their breaking point, vibrating so violently they become a metallic blur. Every sound frequency is recorded. A single discordant note indicates a hidden structural flaw that the AI must identify. Then, the real-world trial, the Ghost Run. A 2,000-kilometer sprint across the Gobi Desert with 0 passengers. The train is pushed beyond its commercial limit, hitting 480 kilometers per hour to test the ultimate stability of the vortex cooling system. Dust storms, extreme heat, and sub-zero nights, the CR450 must remain a silent, steady sanctuary amidst the chaos. Inside the control car, thousands of data points stream to the cloud, creating a permanent digital record of the train's health. Certified, the final stamp of approval. The machine is no longer a prototype. It is a predator of the rails. 106. The CR450 is no longer just a machine. It is a tectonic shift in global logistics. By shrinking the distance between megacities, it creates a 1-hour economic circle for over 400 million people. Time is the most expensive commodity on Earth, and the CR450 just gave it back to us. Beyond speed, it is a triumph of green engineering. Every kilometer traveled emits 90% less carbon than a commercial flight.
As the sun sets on this breathtaking landscape, questions remain about the environmental impact of the new railway expansion.
The technology developed here, from the magnesium alloys to the AI brains, is already leaking into other industries. Aerospace, electric vehicles, and renewable energy grids are all being transformed by the quantum leap of the CR450 project. It is a testament to what happens when humanity refuses to accept the impossible. 453 kilometers per hour on steel rails. A dream that once lived only in equations is now screaming across the horizon. This is the legacy of quantum K manufacturing, dissecting the giants that shape our world. As the sun sets on the age of fossil-fueled flight, a new dawn rises on the age of the sonic bullet. Will this technology spread to every continent? Or will it remain a solitary crown jewel of the East? One thing is certain: the race for the next 500 kilometers has already begun. Don't just watch the future. Understand the engineering that builds it. This is Quantum K Manufacturing. Subscribe and join us as we explore the next mega project that will redefine human history.